All right, today we're going to be discussing 8.3 rational functions, and you'll see here at the top we have three different types of functions that we're going to talk about today. We have continuous, we have removable discontinuity, and we have non-removable discontinuity. And so we're going to talk about those in detail today. You'll see here in this graph that we have a continuous function, and all that means is that once it starts, it doesn't stop. And so this function here can be represented by the equation x squared over x squared plus 1. Now an example of removable discontinuity is given here. You'll see we have a linear function, but there is a hole in the graph. And the way we get this is we have y equals x plus 3 times x plus 2 over x plus 2. When these two pieces cancel, that is what creates our hole at x is equal to negative 2. So we basically set this denominator that cancels equal to 0, and then we would get negative 2. Now for our last form of discontinuity, we have non-removable discontinuity, and that is where there is not a hole in our graph. So here we set our denominator equal to 0. So you can write that on your papers if you would like. Set denominator equal to 0. So we're going to say x minus 2 equals 0, and that here is actually going to be our vertical asymptote. Our vertical asymptote at x equals 2, as you can see is sketched in the graph approximately right here. So one thing we want to note is that points of discontinuity occur where a hole, break, or jump occur in a graph. So we can have a hole like in this second graph, a break, or a jump. So let's work a couple examples. We're going to see if they are continuous or if they have a point of discontinuity. So for number 1, we have 1a. Our function is y equals x plus 3 over x squared minus 4x plus 3. So the first thing we want to do here is we want to factor the denominator. Now remember, we're looking for two numbers that multiply to be 3 and add to be negative 4. So those numbers are going to be negative 1 and negative 3. When we rewrite this function then, we will have x plus 3 over x minus 3, x minus 1. Since nothing cancels, we have our vertical asymptote being x equals 3 and x equals 1. Notice we take the opposite sign of these values. It's as if we set them equal to 0. We just skip that step. And we can say these are points of discontinuity that are non-removable. All right, let's move on to number 1b. So here we have the function y equals x minus 5 over x squared plus 1. Now, this equation here, this denominator, we cannot factor that quadratic. So we're going to look at it on a graph. So you'll take your calculator, or if you're learning at home, you can go to Desmos, go to y equals, and we want to have x minus 5 on our numerator. We want to have x squared plus 1 on our denominator, and then we can graph it. And we are going to see as we graph it that that is actually continuous. Meaning there are no breaks, holes, or jumps. We can also look at our table and we don't see any errors, and that also tells us that we are continuous. So let's look at C. Here we have x squared minus 3x minus 4 over x minus 4. So again, we're going to factor this. We want two numbers that multiply to be -4, add to be -3. So in this case, that's actually going to be what? -4 and 1. So here we'll have equals x minus 4, x plus 1, all over x minus 4. These two cancel. We're left with x plus 1. So because we were allowed to cross out that x minus 4 on our denominator, that means we have a whole. We'll set the x minus 4 equal to 0 and solve. Left with x equals 4. And so we'll write here we have a hole in our graph at x equals 4. And this is removable. Point of discontinuity. Okay, for our next few examples, we're going to find the vertical asymptotes of these functions. And so what we're going to do here is we're going to look at the denominator. If it's not already factored for us, we're going to factor that. And then we're going to set the factors equal to 0 and solve. So you'll see here on option A, we've got x minus 2 times x minus 3. We're just going to set each of those factors equal to 0. If we solve those out, we have x equals 2 and x equals 3. So that is where we will have our vertical asymptotes. X is 2 and 3. We'll do the same for the next two. So here on option B, try this one on your own. If we go ahead and we look at these, we'll set x minus 1 equal to 0 and x plus 3 equal to 0. Solving, we get x equals 1 and x equals -3. Our vertical asymptotes then are at x is equal to 1 and -3. All right, for option C though, you will see that we actually have x minus 2 on the top and on the bottom. So instead of creating our asymptote, that's actually going to create a hole in our graph. We'll be left then, once we cross those out, with 1 over x plus 3. And so we can say we have a hole in our graph at x is equal to 2. We have a vertical asymptote at x is equal to -3. When we discuss horizontal asymptotes, we want to look at the greatest degree on our numerator and denominator, and we'll compare those. And so here you'll see that we have x to the power of m, x to the power of n. Those are just representative of what numbers will be there. Now, if m is less than n, then our horizontal asymptote will be at y equals 0. If m is greater than n, our horizontal asymptote will not be there. We will not have one. And if m is equal to n, then it will be at a over b. And so those are those coefficients on our leading term. So if we go over to the next page, we'll have a few examples. All right, example 3a, you'll see here that our value 2 is our a, and there's no number written in front of x, so that, remember, is an assumed 1, and that will be our value for b. Now, since in this example m is equal to n, because both of our leading coefficients have a degree of 1, then our horizontal asymptote is going to be at y equals a over b, which is the same here as 2 over 1, or just 2. On example B here, you'll see that m is equal to 1, and n is equal to 2. So we actually have a situation where m is less than n. And according to our previous page, when this happens, our horizontal asymptote, we're going to have y equals 0. So it's as simple as that. For example number C, you'll see that m is equal to 2, n is equal to 1, And so we have an m greater than n. That means that we have no horizontal asymptote.